Remember high school math class? Well, it turns out that a single elegant equation from that class is secretly shaping the world all around us, from the bridges we cross to the satellites we launch into space. So today, we're going to decode the hidden power of the quadratic equation.
So, what in the world could launching a satellite, engineering a massive bridge, and maximizing a company's profit possibly have in common? I mean, at first glance, they seem worlds apart, right?
Okay, first up, you've got this immense challenge of calculating a satellite's path. Get that calculation wrong, even by a little bit, and you're looking at a very, very expensive piece of space junk.
And then think about the monumental task of designing a bridge. That beautiful, elegant arch, it's not just for show. It's a precisely calculated curve engineered to handle incredible forces.
And finally, we have the high-stakes world of business. How do you actually find that perfect sweet spot between your price and your sales to make the most profit without accidentally going broke?
Well, the answer, the thing that ties all of these together, it's a single, incredibly powerful concept from math, the quadratic equation. Let's start by decoding this fundamental curve. So, the name itself comes from the Latin word quadratus, which means square. And that's because the absolute star of the show here is that little squared term, the variable raised to the power of 2. Whenever you graph one of these, you always get this beautiful, symmetrical, U-shaped curve we call a parabola. And here it is. This is the standard form. Think of it as the fundamental blueprint. Every single real-world problem we're about to tackle gets boiled down to this exact structure. The real magic, though, is figuring out what A, B, and C actually mean in the real world.
Now, what's really interesting here is just how much power is packed into that one letter, A. If A is a positive number, your parabola opens up, kind of like a smiley face or a bowl. But if A is negative, the whole thing flips upside down. It becomes an arch. So that one little sign, positive or negative, it literally dictates the entire shape of the problem you're trying to solve. Okay, so that's the theory. Let's get to the fun part and see how this exact blueprint is put to work solving absolutely mission-critical problems in some major industries. All right, our first stop, civil engineering. I want you to imagine you're on the team building something massive, like the Chenad Bridge. You absolutely have to know the highest point of that huge supporting arch. Well, engineers model the curve of that arch using this exact quadratic equation. And see that A value? It's negative 0.012. It's a negative number, and that's why it's an arch that opens downward, just like we talked about. Y here is the height, and X is the distance across. You see, the highest point of any downward-facing parabola is called its vertex. And guess what? There's a simple, super elegant formula to find it. You just calculate negative b divided by 2 times a. This little formula right here, it's the whole key. So you just plug in the numbers from the model, and boom. The math tells you, without a doubt, that the maximum height of that arch is exactly 30 meters. No guesswork needed, just a perfect, precise calculation. Okay, let's switch gears and jump over to manufacturing. Imagine you're a manager at a huge company like Tata Motors. You've got a really critical question. What are the minimum and maximum number of parts we need to produce to avoid losing money? These are your break-even points. Okay, so this is what their profit function looks like. Here, P stands for the profit you make from selling X number of parts. And breaking even, well, that just means your profit is 0. So what do? We set this whole thing to equal 0. Now, those points where the profit hits 0, in math, we call those the roots of the equation. If you were to graph this, it's literally where the parabola crosses that flat horizontal x-axis. Finding those 2 spots gives the manager their operational sweet spot. You do the math, and it spits out 2 numbers, 25 and 375. So what does this mean? It means if they produce less than 25 parts, they're in the red. But, and this is the really important part, if they produce more than 375, they also start losing money again, probably because of costs like overtime or extra materials. That sweet spot, the profitable zone, is right there in between those 2 roots. All right, for our last example, let's go to aerospace and defense. This is about as high stakes as it gets. An engineer absolutely needs to know the exact moment a projectile, say a test missile, is going to impact the ground. The height of that projectile, which we'll call h, over a certain amount of time, t, is described by this very equation. And what does hitting the ground mean? It means the height is 0. So again, we're solving for when this whole thing equals 0.
But sometimes the numbers are messy and you can't solve it easily. That's when we pull out the big gun, the quadratic formula. This thing is a universal tool. It can find the roots of any quadratic equation you throw at it, no matter how complicated the numbers look. So we just take our values for A, B, and C from our model, plug them into the formula, and it gives us the precise answer we need. The projectile is going to hit the ground at almost exactly 40.05 seconds. Think about how critical that calculation is for safety, for collecting data, for everything. Okay, so let's take a step back. We've seen these equations build bridges, map out profits, and track projectiles. Let's zoom out now and really connect all these dots to the bigger idea. So the crucial point is this. What you see here is the direct translation from the classroom to the real world. That thing you learned called finding the vertex, that's exactly how an engineer figures out the maximum height of a bridge. And finding the roots, that's not just some random homework problem. It's literally how a business calculates where it starts making money and where it stops. See, these concepts aren't just abstract ideas. They are absolutely essential practical tools.
And that, right there, is why this math matters so much. It's more than just a bunch of formulas. One source put it perfectly, calling it the fundamental vocabulary to interface with the physical universe. It's basically the language we use to describe our world, to translate the curved, messy reality of things like gravity, motion, and even profit into clean numbers that we can actually work with. So from your old school textbook all the way to the cutting edge of modern industry, the logic of the parabola is absolutely everywhere. And understanding it, well, that's not just about passing a test. It's like gaining a superpower to model, predict, and even shape the world around you. So I'll leave you with this question. What problems are you going to solve with it?